So let's talk a little bit about geologic activity and the atmosphere. What drives geological activity for a terrestrial planet is the internal heat. You need something that is going to cause enough heat that things will be melted so that they can shift around. Well, the heat for the Earth comes from three different sources. Some of it is actually left over from the formation of the Earth, specifically through the process of accretion. So if you remember back, accretion is this process of small things slamming together. Well, as they slam together, that's going to release a lot of energy, which means they're going to heat up. We have very strong evidence that early on, the entire Earth was actually completely liquid. The whole Earth was molten because of the heat from accretion. That's part of it. Another source of that heat is from chemical differentiation. Chemical differentiation is the process of things separating based on density. A great example of this is Italian dressing. If you've ever seen Italian dressing that has been sitting for a while, it separates. The heavy herbs settle on the bottom, then you get a layer of oil and then a layer of vinegar because of the changes of density. Well, a similar process happened to the Earth. The heavier elements, iron, sank down to form the core, and the lighter material, the rock, floated out to form the mantle, and then the lightest stuff floated out to form the crust. Well, in this process, we have some stuff sinking down and some stuff floating out, which leads to a lot of friction and therefore heat. So some of the heat that is in the interior of the Earth is left over from this period of chemical differentiation. Now, just those two sources aren't enough to explain all of the heat that drives the Earth today. The rest of it is actually caused due to radioactive decay. So we mentioned there are radioactive isotopes. When these decay, they release energy, which is going to heat up the surrounding rock. So the reason that the interior of the Earth is as hot as it is today, some of it is left over from accretion and differentiation, but there's a lot of it that is being supplied due to radioactive decay. Now, the size of a planet is going to correspond to how long it's going to keep in that heat and therefore remain geologically active. The Earth is the largest of the terrestrial planets, and because of that, it has a large volume, so it's been able to hold on to a lot of heat for a very long time. However, as we get to smaller objects, for example, Mercury or the Moon, these are very, very small, which means they had a small volume in the interior and a relatively larger surface area, which means that it was able to lose a lot of that heat to space. So as we look at Mercury and the Moon, both of these appear to be geologically dead. In fact, as we've done surveys of them, there appears to be no evidence of any geological activity. By geological activity, I mean volcanism or tectonics, the shifting of the crust on the Moon. And only recently have we found the first evidence of a possible ancient volcano on Mercury. But this does not appear to have been active for a very long time. So the size of a planet is going to determine how quickly it loses its heat and therefore how long it's going to remain geologically active. Now, when we look at the Moon is very small and, as I mentioned already, appears to be geologically dead. One way of telling how old the surface is by looking at the number of craters. As we look out the Moon, it is covered with tons and tons of craters. This is because it has no processes to remove or to cover up those craters. So a crater forms, and it stays, and then another crater forms, and it stays. And this process has been going on for over 4 billion years, and because of that, the Moon is very, very heavily cratered. When we compare that to the Earth actually has relatively few craters, and that's because the Earth does have processes to destroy craters. We have volcanism, which, through the flow of lava, will cover up old craters. We have plate tectonics, and in the process of plate tectonics, we're constantly destroying old crust and creating new crust, which is going to remove craters. And the Earth also has weathering and erosion. Because of the Earth's atmosphere, we're constantly causing high regions to be broken down and fill in low regions, which can cover up ancient craters. So the Earth is geologically active, and because of that, we see that it has very, very few craters. The Moon is geologically dead and has been for a very, very long time, and because of that, it actually has lots and lots of craters. We can actually use this idea, and specifically it's referred to as crater counting, to get a feel for how old a surface is. All right, here is another thought question for you. Which object should have the most geological activity? A, Mars, B, an asteroid, C, Earth, or D, the Moon? Go ahead and think about it, and we'll discuss in just a bit. All right, so the amount of geological activity is going to be related to the amount of internal heat, and the amount of internal heat is going to be related to the size. The larger the object is, the longer it's able to maintain the internal heat, and therefore the more likely it is to be geologically active. So an asteroid is super tiny, not going to be geologically active. The moon is also small. It's bigger than an asteroid, but it is still small and has lost most of its heat, so we expect it to be geologically dead. Mars is larger than the moon, and as we look at Mars, we know that it has been volcanically active, at least in the past. Whether or not it's still volcanically active is an ongoing question. We have found some lava flows that are only a few million years old. However, we haven't seen anything more recent than that. So was that the last eruption it's ever going to do, or is it going to have a couple more eruptions in a couple more million years? This is an ongoing question. We just don't know. Is Mars actually geologically dead now? But we do know that it was geologically active more recently than the moon. Earth is the largest of all of these objects, and therefore it has retained the most heat for the longest time, and we see that the Earth is still geologically active. So we'd expect Earth to be the most geologically active. The correct answer is C. As we look at a planet, we can actually figure out the temperature that it should have based on the amount of energy that it gets from the sun and how much energy it then radiates back out into space. This balance between how much it gets and how much it gives off is called the equilibrium temperature. Now, part of what goes into the equilibrium temperature is how reflective the planet's surface is. A planet that reflects a lot of light means that it's not able to absorb a lot of that energy. So we expect a planet that is highly reflective to actually be cooler. A planet that is darker, that absorbs a lot of that energy, we expect to be slightly higher. Now, the index we use to determine the reflectivity, or that we use for reflectivity, is the albedo of a planet. So a planet with a low albedo is going to have low reflectivity, which means it's going to be dark and therefore absorb a lot of energy and therefore be warmer. A planet with a high albedo means that it is highly reflective, which means it's going to reflect a lot of that energy back into space, and we expect it to be slightly cooler. Well, as we take into account these ideas of reflectivity and how much energy the Earth is getting and radiating into space, we determine the equilibrium temperature. The equilibrium temperature for the Earth is about -19 Celsius or -2 Fahrenheit. What that means is that there should be no liquid water on the Earth. We know that that's not the case. There's lots of liquid water on the Earth. That is why the Earth is habitable. The actual surface temperature is between 14 degrees Celsius and 57 degrees Fahrenheit. The difference between the equilibrium and the actual is caused by the greenhouse effect. I'm hoping you've heard of the greenhouse effect previously, but the general idea of it is that there are certain molecules in our atmosphere that are transparent to visible and ultraviolet light, but interact very, very strongly with the infrared. Some of these molecules are water vapor, carbon dioxide, and methane. So what happens is that the light from the sun comes in and hits the ground. Some of it is immediately reflected, meaning it goes back off into space and doesn't do anything. But some of it gets absorbed, which causes the ground to heat up. As the ground heats up, it is going to then give off more infrared light. Well, this infrared light is going to interact very strongly with the water vapor, carbon dioxide, and methane, so that it's not able to just go straight out into space. Instead, it becomes trapped closer to the ground. And because we have more energy trapped closer to the ground, things are hotter than they would be normally. This is the general process of the greenhouse effect, and it's called the greenhouse effect because it's similar to what happens in a greenhouse. Now, what actually happens in a greenhouse is that it is the glass that actually traps the energy. The glass is transparent to visible light, but is opaque to infrared, so the infrared can't get back out. So it traps in the infrared, and the greenhouse becomes warmer. All right, here's a thought question for you. The greenhouse effect is a good thing because it means the Earth is warm enough to maintain liquid water, B, a bad thing because it could heat a planet enough to render it unsuitable for life, or C, it can be both good and bad. Go ahead and think about it, and we'll discuss in just a bit. All right, now that you've thought about it, the correct answer is C, both good and bad. I know that in modern media, we really downplay the greenhouse effect, or at least we say that it's really bad and that's leading to climate change and all sorts of things. And it is. I don't want to say, don't want to disagree with that. However, it's also good in that if we didn't have it, the Earth would be frozen over and there'd be no life on Earth. Now, we're going to see exactly how bad the greenhouse can get later on when we discuss Venus. So it can be good and it can be bad. It's good in that it's kept the Earth warm enough to maintain liquid water and therefore life, but depending on how things keep going, it could get really bad.